Okay, here's chapter 14.2, or section 14.2. And this is, of course, we don't play with anything in chemistry without getting a little mathy with things. So here's the math. We're going to have some specific ways that we can measure concentration, and there's a number of them. The good thing is most of them are fairly similar to each other, and so hopefully we can keep all these things straight. First off is the most important one, typically in chemistry, and this is molarity. Molarity is the number of moles of solute per liter of solution. And its symbol is uppercase M. This is the one that we see all the time in our labs when we're asking for different ingredients, 6M. That stands for 6 molars, which means that it would have 6 moles per liter. In formula form, that is that big M equals moles divided by liters. Okay. And an example here, what is the molarity of a solution resulting from dissolving 50 grams of sodium chloride into 150 grams of water? To do this, first off, we need moles, so we got to turn these grams into moles. We'll do so by saying 50 grams and add 58.5 grams per 1 mole. We would have not that, 0.855 moles of NaCl. And then we want to turn that into, or divide that by the liters of water. Well, we hopefully remember that 150 grams equals 150 milliliters for water, and that to convert from a milli to a base unit, we would divide by 1,000, so that would equal 0.150 liters. And so we're going to divide this by 0.150, and our molarity is 5.7 molar. Why don't you go ahead, try the next example here. Pause the video, and I will solve it in a minute. Okay, so here we have calcium chloride as CaCl2, and that mass is 111 grams per mole. And we're going to do the same thing. We've got to turn this grams into moles. We can then divide it by the volume. So I have 100 grams, and there are 111 grams to 1 mole. And so there are 0.9 moles, and divided by 1.5 liters to get it into molarity is going to be 0.6 molar. The next way we can measure concentration is called molality. Yes, it is a very similar name. Molality is not used nearly as widely. However, there are applications for it, one of which we're going to see later in what we call the colligative properties of water section of this chapter. It's used to kind of determine how much a solute can affect the freezing or melting point of a solution. So anyway, we're going to get to that shortly, so let's not put the cart before the horse. Here is molality. So molality is the moles of solute, but now instead of per liter of solution, it's per kilogram of solvent. And it's really a strange kind of unit, other than it makes our life relatively easy when we go do this freezing point depression and boiling point elevation stuff, and a few other things too. The symbol is a small m. Boy, this pen is not working so well for me. Its symbol is a small m. In formula form, this is small m equals moles per kilogram. Okay, so what is the molality of a solution resulting from dissolving 50 grams of sodium chloride into 150 milliliters of water? And notice that I'm using the same kind of setup for all of these, so you can see we can take the same problem and just kind of relate the concentration in a number of different forms depending on what's most convenient for us. In this case, the 50 grams of NaCl, we have to turn it into moles, and we've already done that up here. We've determined that as 0.855 moles, 855 moles. And we're going to dissolve that into 150 milliliters. Now, 150 milliliters, going back the other way, is 150 grams, which is 0.15 kilograms. Now, this is being done to illustrate a point. In this case, our molality is going to be our number of moles of solvent, that 0.855, and it's going to be divided by the 0.15. Well, look at that's the same thing we did up here for molarity. And so the answer down here is also going to be 5.7 small m. And that is purely only works with water because that water has that 1 gram to 1 milliliter conversion. If we have any other sort of solvent here, the molality and the molarity will not be the same number. But for water, well, it turns out, at least water at 4 degrees Celsius, which we make the assumption that most water is, at least close enough to that. Oh, sorry, this answer should be down here. 5.7 molar. And the next way we can determine concentration. This is used typically for things that have very low concentration. So quite often the applications could be in the medical industry, talking about things in your bloodstream that are in, very minute concentrations. We might use something called parts per million or parts per billion. Parts per million is ppm, and parts per billion is ppb. Those two things are similar to percent. In fact, the name percent, see this parts per billion, cent means 100. So a percent is a per 100, just like a per billion is would be per 1 billion. Parts per million, a percent is per 100. So to determine them, what we do is the same thing we do for any percent we do, where we divide the part by the whole. In this case, the part being the mass of the solute, and the whole is the mass of the solution. And mind you, just keep aware that the mass of the solution is the mass of the solute plus the mass of the solvent. So we have to add those two things together in order to find the mass of the solution. Then we divide the mass of the solute by that mass of solution. And the second step would be to multiply by 1 million for parts per million, and multiply by 1 billion for parts per billion. So just like we would multiply by 100 to get a parts per 100 or a percent, we would multiply by that 1 million for parts per million or 1 billion for parts per billion. So this is going to kind of be a fairly ridiculous answer because I wanted to kind of stick with this same example that we had done previously, and this will be an ungodly amount of parts per million. This isn't a normal application we'd use this particular measure for, but let's go ahead and do it anyway. Concentration of parts per million for a solution that resolves from 50 grams of sodium chloride into 150 milliliters, or we'll just say 150 grams of water. And so I've got my 50 grams of my solute, and I've got in the bottom my 50 grams of my solute plus my 150 grams of my solvent, and I'm going to end up with 50 divided by 200, or 0.25, and 0.25 times 1 million equals 250,000. And so we would end up, in this particular situation, saying that this concentration would be 250,000 parts per million. Again, not a typical application there, but that's how we would run through it. Speaking of percents, we didn't think we were going to escape without talking about percents a little more, hopefully, because we will. So we have a few different ways we might use percents here, depending on application. And we're not going to really concentrate on any of these, but we need to show them, so we'll just go really quickly through this. Okay, the typical percentages used are mass to mass percent, or the mass percent, a volume to volume percent, or volume percent, and a mass to volume percent. And they're done really easily. A mass percent is just the mass of the solute divided by the mass of the solution times 100, and part divided by whole times 100. And volume percent is going to be the volume of the solute over the volume of the solution, and again times 100%. And a mass to volume percent, side thought I'll share with you in just a second, is the mass of the solute to the volume of the solution. And as far as I'm aware, this one is mainly used in medical approaches in the medical field. And that would also be times 100. Just as a neat little thing, with this little percent symbol here comes from divided by 2 zeros, or divided by 100. Because if we wanted to turn this back into the actual decimal, we would have to divide it by 100. So kind of neat little thing that just morphed into that sort of symbol through time. That 0 got slid to the top of the divide sign. Okay, here we go. A couple examples, same situation we've dealt with in all of these. The mass percentage, 50 grams of solute. We have 200 grams of solution, the 50 of the solute, the 150 of the solution, and so again that is 0.25, and then we times 100%, so that solution would be 25% sodium by 25% mass to mass. And we could say volume percent here. That's a really bad question because we wouldn't really have a realistic viewpoint of what the volume of sodium chloride is without looking at its density. So let's just kind of, sorry, I should have had this here, but density of sodium chloride So sodium chloride is 2.16 grams per cubic centimeter. Okay, we can work with that. So we've got our, to the right screen here. Okay, so we've got our 2.16 grams per cubic centimeter. We're going to take this and we're going to turn it into cubic centimeters. Remember, a cubic centimeter is a milliliter, so that'll put our volumes into the same unit, so we can do this. By the way, they just have to be in the same unit. It can be grams, kilograms, whatever, as long as the top and the bottom are the same. So we got to get this to be in milliliters. And so we're going to say 50 grams. And there are 2.16 grams per cubic centimeter. And then if we want to be formal about it, of course, we can say that for 1 cubic centimeter, there's 1 milliliter. And we will find out that in sodium chloride, we would have 23.7 milliliters of sodium chloride. So now we've got our volumes and we can solve this. On any of these problems, we're going to assume there's the mass of our solute, or the volume, excuse me, of our solute. And now we need the volume of the solution. We're going to assume that the volumes are additive. They aren't always, but we have to start somewhere. So we're going to make that assumption at our level of chemistry. Here we go. We've got 23.7 for the solute. We've got another 150 for the solvent. And so we have a 173.7 milliliter total solution volume. And we end up with this 0.136, times it by 100%, and we would have 13.6% NaCl volume to volume. And we can also, by the way, abbreviate this as V to V. We could abbreviate this as M to M. And though you need to have those on, because look, if I just asked what's the percent of sodium chloride in the solution, well, we have two very different results depending on if we're looking by volume or by mass. Okay, if that wasn't enough math for you yet, I've got one more trick up my sleeve for this section. Don't worry, we're almost done with it. But this is the changes in concentration. So quite often we'll mix two solutions together that have different concentrations in order to achieve a particular concentration we're looking for. So there's a formula that controls that. If we take the moles of the solution 1 times the volume of solution 1, and we add that to the second solution, we're adding the moles, molarity times the volume. That will give us the molarity times the volume of our final solution. Well, because molarity times volume is moles. And if I go moles plus moles equal final moles, well, that should make some sense. Yeah, let's see this in practice. I have 200 milliliters of 4 molar hydrochloric. And again, this is a nice, neat formula, and my units can be anything as long as they match. It'll output whatever units I put in. So I can say I have 200 milliliters, and that is of 4 molar hydrochloric acid. And then I add it to 100 milliliters of 2 molar hydrochloric acid. My resulting concentration would be, well, wait a minute, I've got two unknowns. How do I know how to multiply those? Well, you don't really have two unknowns. Again, we're going to assume that all the volumes are additive. So this volume of the final solution is the volume of these two solutions added together. Or in other words, we now have 300 milliliters of some solution with an unknown concentration. And so I'm going to say, well, I've got 800. Plus I've got 200, and so I've got 1,000 on this side. And I'm going to divide that by the 300, and I would find out that I would have a 3.33 molar solution at the end. So let's see another example of this, but one that, ooh, that nasty cursor out of the way. Another example of this, but one in which we're using just water. So let's start out with, we've got some 14 molar sulfuric acid, and we've got 150 milliliters of it. Now we want to add some amount of water. Okay? We don't know what that amount of water is, but we know that water is pure, or we're assuming pure water, has a molarity of 0. There's nothing dissolved in it. So our second term, the concentration of our second part of our solution is 0. We don't know what the volume is, so we'll call it X. Doesn't matter because 0 times anything is 0 and drops out of our problem. And then over here on the right-hand side, we have a solution with a 3 molar concentration. And we want to know what volume it is. So we will say that volume is X plus 150. Why X plus 150? Because I said this volume was X. And we need the volume of the solution, so we need to add these two things together. Okay, now algebraically you might not like that so much, but we'll show you how to chop through it here, and it's not too bad. So first off here, 14 times 150 is 2100. And that's going to equal this 3 molar times this thing. Well, I'm going to divide by that 3 to get rid of it, and then I've just got X plus 150. And here is 700 equals X plus 150. And now I subtract the 150 from both sides. So I find out that X equals 550 milliliters of water. That's how much water I have to add. Go ahead, try that one. Pause the video. Okay, so we've got 18 molar hydrochloric with 100 milliliters of it. We're going to add 900 milliliters of water to end up with 1,000 milliliters of unknown concentration. That term drops out. We end up with 1800 equals 1000 X. X equals 1.8. And that is molar. 1.8 molar. Okay, that is it for video 14.2. See you back for 14.3.